Welcome. In this video series, we'll be diving into one of the most popular resources for aspiring software engineers called Cracking the Coding Interview by Gail Lackman McDowell. So, if you're preparing for a technical interview, this series will help you go through all the patterns, questions, and solutions of programming questions asked in the interviews. We'll start with the chapter Linked List and go through its questions. Our next problem is about removing duplicates from an unsorted linked list. So here, given a linked list, you need to write a function to remove any duplicate nodes. After removing duplicates, the list should contain all unique elements. Here, we'll discuss two solutions. One using extra space and another using without any additional spaces. In the first solution, we'll use a hash table to keep track of the nodes we have already seen. We iterate through the list, and if we encounter a node with a value that's already in hash table, we remove it by updating the previous node's next pointer. Here is an implementation of this in C++. In this solution, we use an unordered set to track the values we have already encountered. If we find a duplicate, we simply remove it from the list. The solution here has a time complexity of order of n and a space complexity of order of n due to this unordered set, where n is the number of nodes in the list. In the second solution, we'll solve the problem using without any extra space. This approach involves two pointers, a current pointer and a running pointer. So, for each node, the current pointer checks all subsequent nodes for duplicates. If a duplicate is found, we remove it. Here, while looking at the code, we can see we use a nested loop to compare each node with all subsequent nodes. If we find a duplicate, we remove it. This solution here has a time complexity of order of n square, but a space complexity of order of 1, making it more space efficient than the first solution. Next up, we have a classical problem often asked in interviews, finding the kth to last element in a single linked list. The goal here is to return the element that is k positions from the end of the linked list. There are several ways to approach this problem, and each has its own advantages, but we'll go through three different solutions. Here are some hints and clarification that you can discuss with your interviewer. So, when solving this problem with an interviewer, it's important to clarify a few points with him. First, what should we return if the kth element is out of bounds? Can we assume that the list is non-empty? Or what solution would they prefer to implement? In the first solution, if we know the size of linked list, we can directly calculate the position of kth to the last element. Specifically, we have to find the element at position length minus k. Here's the code of it in C++. Here, the first approach calculates the length of the list and traverses it again to reach the length minus kth node. Here, the solution has a time complexity of order of n and a space complexity of order of 1. However, it requires two passes over the linked list, one to find the length and other to find the kth to the last element. Here is a second approach, which is a recursive approach. In this solution, we use recursion to find the kth to the last element. The idea here is to traverse the list recursively until the end and then backtrack while keeping the count. So whenever the count reaches k, we return the corresponding node. Here, as we can see from the solution, it makes a single pass through the linked list with a time complexity of order of n. However, it uses order of n stack space due to recursion stack. This solution is elegant but may not be suitable for very large lists due to potential issues with stack overflow. The third solution is the most efficient solution, in which we use a popular technique called two-pointer technique. Here, the first pointer is moved k steps ahead, and both the pointers move together until the first pointer reaches the end of the list. At this pointer, at this point, the second pointer will be the kth to the last element. This method, as we can see from the code, will be time efficient and space efficient, with a time complexity of order of n and a space complexity of order of 1. It is an elegant and optimal solution for this problem. Deleting middle node. Deleting a node from the middle of linked list. The next problem we'll tackle is about deleting a node from the middle of single linked list. The challenge here is that you are given access to the node that you want to delete, not the entire list or even the head of the linked list. So, how can you remove it without having access to the previous node? Some discussions to have with your interviewer. First, clarify with the interviewer if the node to be deleted is not the last node, as this solution wouldn't work otherwise. Ask if there are any specific constraints, such as whether the list might contain duplicate values or could affect testing the correctness of solution. Explain the implications of this approach, such as how the original node's identity is lost when data is overwritten. Solution. The solution is to copy data from the next node. The trick here is to copy data from the next node into the current node and then delete the next node. This effectively removes the current node from the list. Partition. Rearranging a linked list around a value. In this problem, we need to partition a linked list around a value x such that all the nodes with values less than x come before nodes with value greater than x or equal to x. It's important to note that if x is present in the list, it should be maintained in the right partition. The order within the partition here need not be maintained. Solution 1. Using two linked list approach. The approach we'll use involves creating two separate linked lists, one for the element less than x and another for elements greater than or equal to x. After traversing the original list and populating these two lists, we'll merge them to get a final partitioned list. Here, we'll look at the implementation of it in C++. In this implementation, we first iterate through the original nodes. For each node, we decide whether it's going into the before list or after list based on whether its value is less than x or more than or equal to x. Finally, we merge two lists. If the before list is empty, the result is the after list. During an interview, make sure to discuss the following points. First, ask if the order within each partition needs to be preserved, because the previous solution does not preserve the order of nodes relative to each other. Second, clarify what should be done if the list contains multiple nodes with value x. Third, if time permits, mention alternative approaches or optimizations, such as doing the partition in place without using extra space for additional linked list. Sum list, adding numbers represented by linked list. In this problem, we are given two numbers represented by linked list, where each node contains a single digit. The digits are stored in reverse order. Here, meaning that one's digit is at the head of linked list, tenth digit is at the second node of linked list, so on and so forth. Our task is to write a function that adds these two numbers and returns the sum as a linked list. Let's first tackle the problem where the digits are stored in reverse order. Part 1. Adding numbers in reverse order. To add the two numbers, we traverse both the linked list, adding the corresponding digits. If the sum exceeds 9, we carry over the 1 to the next node. This can be done recursively or iteratively. Here, we see the implementation of it in C++. In this implementation, we add the digits from the to list along with an carry from the previous step. If the sum of two digits exceeds 9, we carry over the 1 to the next node. The recursion handles the addition until both the lists are exhausted and any remaining carry is added as a new node. Part 2, Digits stored in a forward order. Here, we'll consider the case where digits are stored in a forward order in the linked list. This time, we need to handle the numbers from the most significant digit first. To do this, we can pad the shorter list with zeros and use a recursive approach to calculate the sum from the end of the linked list to the beginning. In this approach, we first pad the shorter list with zeros so that both lists have the same length before passing it into the function addList. We then recursively add the list from the last node to the first, keeping track of the carry. Finally, if there is a carry left after processing all the nodes, we add it as a new node at the head of the linked list. Palindrome check in linked list. In this problem, we determine if the linked list is a palindrome or not. A palindrome is a sequence that we discussed earlier that reads the same forwards as it is backwards. We'll explore three different approaches to solve this problem. Solution 1. We reverse and compare. The first solution involves reversing the linked list and then comparing this reversed linked list with the original linked list. If both the linked lists are identical, then it is a palindrome. The second approach uses a stack to reverse the second half of linked list while traversing. By comparing the nodes of the first half with the reverse second half, we can determine if the linked list is a palindrome. Here, we use a stack to store the first half of the linked list elements, then we compare these elements with the second half of its list. If they match, then it is a palindrome. Solution 3, which is a recursive approach. The third approach uses recursion to check if the linked list is a palindrome. We pass here the node reference as we recursively check the list from the end to the beginning. In this approach, we traverse to the end of the list and then check each node's value while unwinding the recursion. If any node does not match, the list is not a palindrome. Discussion to have with your interviewer. When discussing the problem with an interviewer, consider asking three questions. How should you handle cases where the list is empty or has only one element? Are there any constraints on the space complexity that we need to consider? How should the solution handle larger lists for performance constraints? In this problem, we need to determine if two linked lists intersect and return the intersecting node. Here, the intersection is defined by reference, meaning if we need to find if two nodes in the first list is the same as the exact same node in the second list. Here, to solve this problem, we'll explore two solutions. Solution 1. Length and tail comparison. The first approach involving comparing the tails and length of both linked lists. If the tails are different, then there is no intersection. If they are same, then we adjust the starting points of both the lists based on their lengths to find the intersecting point. Here, as you can see, we first determine the lengths and tails of both lists. If the tails are same, we adjust the starting pointer based on the length difference and traverse both the linked lists until we find an intersection. Solution 2, which is a stack-based approach. It involves using a stack to find an intersection. Here, we'll push all nodes from both the linked list onto separate stacks and then pop until we find a common node. Here, as you can see from the code, we are pushing all the nodes from each list into a separate stacks. By comparing nodes from the top of the stacks of both stacks, we can find the intersection node. Some discussions to have with your interviewer. First, how should you handle cases where one or both of the lists are empty? Second, what is the maximum allowable length of the list? Third, are there any constraints on memory usage or performance? The next problem is loop detection in a circular linked list. In this problem, we'll given a circular linked list where a node's next pointer points to an earlier node, creating a loop. Our task is to determine the start node of the loop. So let's dive into the solution using a classical approach using two pointers. We'll use Floyd's cycle detection algorithm, also known as tortoise and hare algorithm, to solve this problem. So here how it works. First, we initialize two pointers, slow and fast. Move the slow pointer one step at a time and fast pointer two steps at a time. If there is a loop, the fast pointer will eventually catch up to the slow pointer. Here, this happens because fast pointer is moving faster and eventually enter the loop and collide with the slow pointer. Once the slow and fast pointers collide, we move the slow pointer back to the head of the linked list while keeping the fast pointer at the collision point. Now, we move both pointers one step at a time. The node at which they meet is the start of the loop. Here's the code of detecting the loop in a circular linked list in C++ using the steps discussed in the previous slide. Some hints and discussions to have with your interviewer. First, what if the linked list is very large and memory constraints are tight? Are there any specific performance constraints or requirements? Third, how should you handle cases where an empty list or a list with no loop? That wraps up our review of the essential coding interview questions from chapter 2 of linked list. If you have any questions, please comment down in the comment section. That's it from chapter 2. Thank you. Thanks for watching.